I am the remote. I give commands to the remote. Like, you press that. All right, so next unit. It's a very small unit. The unit is momentum, and momentum in collisions. So momentum is the practical application of Newton's three laws. Okay? For every reaction, there is an opposite and equal reaction. Force equals mass times acceleration. In fact, it wasn't actually force equals mass times acceleration that Newton came up with. He talked about the time rate change of momentum. In other words, how momentum changes. So I have up here the OG. I think I get this out of the way. I got the OG dynamics track up here. This was the original dynamics track. It's 2.5 meters, aluminum extrusion. And then these guys were 250 gram carts, and they got magnets built in on one side and Velcro on the other side. These are the carts that the manufacturer of your carts actually cloned. So these are the original dynamics carts. Well, for my generation. There was actually one before these, but they didn't have built-in magnets and Velcro. And you bought them as a set. There's a green car and the blue car and red car.
So does transfer damage to each car upon collisions?
Yes, actually. So when a car is moving towards another car, we call it the attacking car. And the car that gets hit is called the target car. So here, the blue car is going to be the attacking car, and the red car is going to be the target car. And then red is the attacking, blue is the target. And because these guys are the same mass, they actually transfer all of their momentum from one to the other. It's pretty slick. It's a nifty physical phenomenon you don't see very often. Pretty much, what's the only place you might see a collision that's like this?
A train.
Definitely not a car crash. Car crashes are more like this. Yeah. Yeah, billiard balls. So billiard balls are made to be the same mass. So if you hit them without any spin, one comes to a rest and the other one picks up all of its momentum and goes. That's part of the fun of billiard balls. It would be a much stranger environment if the balls weren't all the same mass. Because if they weren't all the same mass, then you have different kinds of collisions. So for instance, let's look at this guy. I've now doubled the mass of the blue car. When I roll the blue car, which is the attacking car, into the red car, which is the target car, take a look at what happens to the red car. And think what happens to the blue car. Yeah, it continues on. And if you make the attacking car less massive, watch what happens here. Oh, yeah. Sometimes it just falls off the track. Yeah. Momentum is transferred, but this guy goes backwards. So, backwards it goes. Okay. And then once again, if you're like, something's wrong with the cars, again, if you double the mass of both of them, you're back to the original situation where all of the momentum is transferred. Pretty cool, huh? I love these things. Anyway, so here's a fun diagram. Again, when equal masses, they transfer momentum. Now, the important thing to remember about momentum is a vector. It's critically important to remember that momentum is a vector, hence the little half arrows that are sitting over the P, the V, and the F. Momentum is given the letter P, little p, not to be confused with big P, which is pressure. So momentum is little p, and this is called the impulse momentum theorem. This is the impulse momentum theorem. So this is momentum, P, mv is momentum, and ft is impulse. Impulse. You gotta control your impulses. Yeah, they're supposed to be equal, but something went sideways. What this basically means is the change in momentum is equal to the mass times the change in velocity is equal to the change in force, change in time. Okay. We're going to assume the mass for a single object is not going to be changing in this class. Okay. We're just going to assume that all mass is pretty much constant. That way the math actually makes it a little bit easier. Okay, now, if you know what velocity is, you know what mass is, right? Mass, this is 0.25 kilograms, and this is 0.25 kilograms. So, you know what velocity is. So, it should make sense if this is positive velocity and this car has positive velocity and it comes to a rest, then this car has to have positive velocity. Make sense? And if this car has negative velocity and it comes to rest, then this car must have negative velocity. Cool? All right. Now something kind of weird happens when you're attacking. I'll make this one heavier. When your attacking car is lighter than your target car, watch what happens. Yeah. This car comes in with positive velocity, goes out with negative velocity. This car now has positive velocity. So
So does it you said the receiving car, what was it?
target car?
Target car, sorry. So the target car, does it absorb all the energy plus a little extra, causing it to...
Okay. Let's move away from the idea of energy for just a second and talk about absorbing momentum or transferring momentum. So we are going to talk about energy, because energy is an important part of collisions, and it's what we just learned about. But let's talk about momentum.
Okay.
Momentum must always be conserved, even if you go in with a positive velocity and you come out with a negative velocity. That means you go in with a positive momentum and you come out with a negative momentum. And we're going to do a bunch of exercises on converting momentum. Momentum is always conserved. Energy, not so much. Because look what happens. Turn them around. I'm going to roll them towards each other. Okay? I'm going to go, woo, and they're going to stick. Remember, energy is not a vector. Energy is a scalar. So if this one goes this way, does it have energy? Does this car have kinetic energy going this way?
Yeah.
Yes. Does this car have kinetic energy going this way?
Yeah.
Yes. So do they have negative energy? No. They both just have energy. Energy is a scalar. There is no negative energy. You can have a change in energy, which is work, that can be negative, but energy is just energy is energy. So watch what happens when this one has energy and this one has energy. Do they have energy now? No. What happened to their energies?
They were, well, you said it wasn't a vector, they canceled each other out, but they're absolute, like, distance from zero, scalar, like you said. That's weird.
Yeah. So we have plus E and plus KE plus KE equals 0. KE plus KE equals 0. Energy is not always conserved. Energy can be lost in this situation. In this case, it's lost in the form of friction. The Velcro pads have a tremendous amount of friction. So if you were to shine a really precise thermal detector at these things, you'd be like, hey, they got warmed up. Because they did. They got warmed up. The energy of motion here and the energy of motion here went boop, and it was converted to heat right there. Okay. This is called an inelastic collision. An inelastic collision is when energy is lost. So an inelastic collision is when energy is lost. Now an elastic collision is when energy is not lost. This one comes in with KE, this one comes in with KE, and they go away with KE. So the KE before the reaction, or before the collision, is the same as the KE after the collision. So when energy is not lost, we call it elastic, like the elastic in my pants. So inelastic, energy is lost. Elastic, energy is conserved. But momentum will always be conserved. Does this make sense? Okay. Let's get right into it then. PowerPoints! PowerPoints, have fun! So again, definition of momentum. Momentum is given a little great, the English letter P. And momentum is mass times the velocity. Here's the weird thing about momentum and your opportunity for greatness. Momentum does not have a named unit. Okay, like a hertz is given is the named unit for a per second, and we have a Newton and we have a joule. Those are all named units. Momentum doesn't have a named unit. So momentum is the product of mass and velocity. What is the unit for mass? Kilogram. And what is the unit for velocity?
Meters per second.
Meter per second. So that's the unit for momentum. Now, if you are just awesome and spectacular, maybe they'll name one after you. First name or last name, who knows? So momentum is mass times velocity. It's a vector quantity. It's equal to the product of the object's mass and velocity. And then force is the time rate change of momentum. That's what Newton wrote. Force is the time rate change of momentum. In other words, it is how momentum changes over time. Anyone in calculus in here? You never really know. Pre-calc? So have you done derivatives in pre-calc yet?
Not yet.
Okay, so I won't go into it then. So we'll divide by time. So if you have kilogram meter per second and you divide by time, different color. I'll just throw that pen on the floor. If you have kilogram meter per second and you divide by time, which is seconds, you're left with kilogram meter per second squared. What unit is a kilogram meter per second squared? Force. And the unit is? No. Newton. Okay. So again, you learned that F equals ma, which is great, which is newtons equals mass, newtons equals kilogram times meter per second squared. Kilogram meter per second squared. The change in momentum, the delta P over delta T, is your force. Okay? That's what Newton talked about. He didn't say F equals ma. What he said was the change in momentum of an object equals force. Force changes momentum. I'll write it really big over here. So, delta P divided by delta T equals force. Equals ma. Make sense? So if force is the time rate change of momentum, and force is mass times acceleration, then mass times acceleration is how momentum changes. Which should make sense, because if you want your car to get more momentum, get more killing power, what do? You accelerate. If you want to build up more strength before you lay somebody out on the football field, you have to accelerate at them. You build up more momentum by accelerating, then you bash into them in a collision. That's what we'll be talking about in a little bit. And you get a concussion, or you break your ankle. Okay? Now, if you rearrange this, you get something kind of interesting. If you multiply the force times time, what you get is the change in momentum equals force times the change in time. And this is the impulse momentum theory. Impulse is the force times time of a collision. Impulse is the force times time of a collision. If I throw a ball, I have velocity, right? Uh-oh. Wait a minute, something's wrong. If I drop this ball, it has a velocity in the downward direction, right? How come it bounced and had a velocity in the upward direction?
Elastic.
Inelastic.
It is an inelastic collision because energy was transferred. If it was elastic and I dropped it from here, where would the ball come back? It would come back up here. It was an elastic collision. Yeah, it is an inelastic collision. Got to be tricky with those. I'd use the egg, but you never know with the egg because eggs are strange. But if you drop it, you have a negative velocity going down. Whee! Boing! And then it comes back up with a positive velocity. Wait a minute. I thought you said momentum was a vector. So if you have a downward momentum before you hit, how is it you have an upward momentum after you hit? I thought you said momentum was conserved. Here's the problem you don't even realize you have. If you drop something and it has a downward momentum because mass times velocity is a vector, nod your head if you realize it. Mass times velocity is a vector. Okay. If you drop something and it has a mass times velocity, which is a vector, going down, and then all of a sudden it comes back up, is momentum conserved? No, because you have a downward vector turning into an upward vector. Momentum's not conserved. You can't have a positive thing turn into a negative thing. That's not conservation. When you walk into the mall with $100 and you walk out of the mall with negative $100, was your money conserved? No, it was not. So maybe this will make more sense. Let's say positive velocity is towards the board. Let's say negative velocity is away from the board. Adam, throw the ball at the board. Throw at the board as hard as you can. Oh, nice. That was multiple collisions. Okay, does that make sense? So when Adam threw the ball, it had a positive velocity.
Harder this time.
As hard as you can. Cool. When it came back, it had a negative velocity. So was momentum conserved? No, it was not. But here's the thing. If you need to resolve that vector problem, which we definitely do, that's where impulse comes in. Impulse is where the ball gets squished into the board and then unsquishes away from the board. Impulse is a neutral quantity that allows the momentum to be conserved. Impulse happens during a collision. Okay? If something is moving, it has momentum. If something is colliding, it has impulse. Does impulse have to be conserved? No, it does not. Momentum must be conserved.
Okay.
Impulse does not. Impulse is just a thing. It's a quantity. And here's the crazy thing about impulse. If I take this car and I slam this car into this car, was momentum conserved? They're exactly the same mass. This one comes in with positive V, this one goes out with positive V. So this guy goes from V to 0, this guy goes from 0 to V. Is momentum conserved?
Yes, sure.
Yes.
But,
Yeah.
So is impulse pretty much just collisions but with friction?
No, just collisions.
Just collisions.
We're going to leave friction out of it for now, just
impulse as
collisions.
well, then?
Yes, there is momentum, impulse, momentum. Momentum, impulse, momentum. Momentum, impulse, momentum. Momentum, impulse, momentum.
Impact.
Momentum, impulse, momentum. Momentum, yeah, like impact. And here's the crazy thing. Newton's third law says, for every action there's an opposite and equal reaction. You know what it really says? During a collision, this car experiences the exact same impulse as this car. So this guy comes in with positive velocity, all the velocity turns into impulse, that impulse transfers to this car, and then all the impulse turns into momentum, mass times velocity. So we have momentum, impulse, momentum, impulse, momentum, momentum, impulse, momentum, momentum, impulse, momentum. Okay. And the force that this car applies on this car, how do they compare? Equal. And the time of collision, this car on this car, and this car on this car, how do the time of collisions compare? Equal. Okay? So the impulse is the same on both cars because the force is the same and the time of collision is the same. Capiche? Verstehen? Geprende? Okay. Questions? Give me a thumbs up if you're ready to move on. We've battened down almost all the concepts we need to learn. Again, momentum is a very, very, this is what we just did. There's your impulse momentum theorem. And if you like to write things down, there you go. A large impulse is required for a large change in momentum. You don't need to write this down, but just pay attention. You need to write the impulse momentum theorem. That's definitely very important. It's on your formula sheet too. So a large impulse is required for a very large change in momentum, which should make sense, right? And a small change in momentum requires a small impulse. Does a large change in momentum require a large force? What do you think? Do you need a large force to have a large change in momentum?
Cool.
I have one vote for no. Maybe you should chat with your neighbor. Think of a situation where you would not need a large force to have a large change in momentum. Can you think of such a situation?
The force has to be applied on the object.
That's something totally heavy, but it's going at a speed.
Mass times velocity. The impulse force times time. So in order to change the direction of the impulse, the impulse has to be large enough to change.
Oh, I got it.
This is where the model breaks down. I don't really know what a cruise ship looks like anymore.
Let's call it a cruise cake, and it looks.
It's a cruise cake. So there's this cruise ship, and here's all the people who are like, norovirus, poop cruise, Okay, of course the people are like 30 feet high. But when a cruise ship comes into port, it has these tiny little pilot ships called tugs that cruise alongside and they guide the ship in. Same thing happens when an oil tanker comes in. Tiny ships guide it in. And these tiny ships, they don't be like, we got a ship about 1 mile out, we better go send a ship. No, the ship is hundreds of miles out, and that's when they send the tug. That's when they send the tug out. Because the tug will apply a very small force to slow the ship down over a very long time.
Oh, kind of like mechanical advantage.
Okay. Does that make sense? So, does a large change in momentum require a large force? No. No, it doesn't. You can apply a small force over a very long time. Now, with a bullet, a large change in momentum requires a small force over a hugely small time. Tiny, 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 tiny. Boom! All that gas expands very rapidly. With a bow and arrow, the time comparatively to launch an arrow is a lot longer. In a gun, it's like bang. In an arrow, it's like whoo. But both have similar killing power. You don't want to be on the business end of either. Okay, car crashes. This is fun. Look at the car. Look at it. Blammo!
Whoa.
Yeah, you know what those things are filled with? Those, if you're in big cities where space is at a premium, they fill up those columns with water or sand or both. Yeah, and then you hit it like kaplowy because water absorbs a lot of energy. Blammo!
I've done that.
At least you landed and planted up right.
Yeah. Okay, so why do we use a seatbelt and an airbag?
I don't.
To reduce the impact force.
Like, ain't no government gonna tell me to use seatbelt, no bag. I get in there and I turn off my airbags right away, stick a knife into the airbag so it can't deploy. So why does it do it?
Take out the seatbelt piece so it doesn't blink out.
So it keeps you in the car, right? No, that's not why.